Good evening, students. Welcome back to Structure of Atom. Yes, in previous class, we've been discussing about the atomic models, and before that, we were discussing about the developments which led Niels Bohr to propose a model of atom. Correct. So today we are supposed to start Bohr's atomic model. Before that, there is one more theory that we are left with. From last 3 days, I'm saying you people I start Bohr's atomic model, but it is taking much time to cover those basic things. That is why. Clear. Otherwise, I would have started. So you people should understand that is our main aim, and that is why I have discussed these many things. Correct. And before starting Bohr's atomic model, let me go for one more last concept, that is Planck's quantum theory, which says that the particle nature of what electromagnetic radiation. That is nothing but my Planck's quantum theory. It is called as what? Planck's quantum theory. See, Planck's quantum theory. Planck's quantum theory. So which also gives idea about what the particle nature of electromagnetic radiation. Right? So what he says that according to his Planck's quantum theory, there are some assumptions, or you can say the postulates. Right? There are postulates. Planck's quantum theory has 3 to 4 postulates, in fact. And among those, the first one, the radiant energy, the energy from those electromagnetic radiation, that radiant energy is not absorbed or emitted continuously, but discontinuously. Okay? So he says the first postulate of Planck's quantum theory, I'm talking about the first postulate, the radiant energy is not absorbed or emitted in continuously, but discontinuously. Not continuously, but discontinuously, in the form of small packets of energy called as quanta. Small packets of energy called as what? Quanta. In case of light, this quanta is also called as a photon. That is his first postulate. Quanta is nothing but quantum of energy, a packet bundle of energy, a small packet of energy. So that's what he said. His first postulate was like radiant energy does not absorb or emit continuously, but discontinuously, in the form of small packets of energy called quanta. In case of light, it is called as what? Photon. So that is his first postulate. Right? So I'll write the first postulate. So please write down these postulates. These are needed here. He said the radiant energy is not absorbed or emitted continuously, but discontinuously. What? Discontinuously in the form of small packets, in the form of what? Small packets of energy called quanta. Called what? Quanta, or quantum of energy. Small packets of energy is called as quanta. In case of light, it is called as quanta. Is called as what? Photon. In case of what? Light. In case of light, this small packet of energy is called as what? Photon. Clear? So this is his first postulate. Clear? And then second postulate of Planck's quantum theory. The frequency which is associated with these radiations, frequency, nu, it is directly proportional to the energy. Or else you can say the radiant energy, the amount of energy, the radiant energy is proportional to what? The frequency of what? The radiation. Means E is directly proportional to what? Nu. Correct? So that is nothing but my second postulate. So second postulate is what? The amount of energy associated with quantum of radiation. I'll write that one. Amount of energy associated. Amount of energy associated with quantum of radiation. With quantum of radiation. With quantum of radiation is directly proportional to. Is proportional to what? Frequency. Is proportional to what? Frequency, he said. So that is his second postulate. Amount of energy associated with the quantum of radiation is proportional to what? Frequency. Okay? So frequency of what? Radiation. Frequency of that particular radiation, you can say. Clear? Radiation or frequency of light. Frequency of light, you can say. So that is expressed as, see, E, energy is proportional to what? Frequency. That is my nu. Energy is proportional to what? Nu. Or else, I can even write it as E is equals to h nu. E is equals to what? H nu. Okay? E is equals to h nu. What is h then? H is Planck's constant. Where h is Planck's constant. It is Planck's constant. Where h is Planck's constant. Clear? The value of this Planck's constant is 6.626 into 10 to the power minus 34 joules. 6.626 into 10 to the power minus 34 joules is the value of what? This Planck's constant. Correct? So this is the second postulate of what? Planck's quantum theory. Remember, amount of energy associated with quantum of radiation is proportional to what? Frequency of the light. So that is nothing but E is proportional to nu. So as to remove this proportionality constant, I got h. E is equals to h. E is equals to h, where h is Planck's constant. So this is the second postulate of Planck's quantum theory. So I will go for the third one. I will rub this. Before that, you write down this. See, first one was the radiant energy is not absorbed or emitted continuously, but discontinuously in the form of small packets of energy. Those are called as quanta. In case of light, quanta is called as a photon. That's it. Right? And the second one, the amount of energy, that energy, whatever I was talking about, the energy, the amount of energy associated with the quantum of radiation is proportional to what? Frequency of the light. It is proportional to what? Frequency of the light. That I can write it as E is proportional to nu. So that is nothing but E equals to h nu. So where h is Planck's constant and the value of h is 6.626 into 10 to the power minus 34 joules. Okay, so this is the second. We'll go for third. Before that, I'll rub these two. We'll go for the third postulate of what? Planck's quantum theory. Planck's quantum theory. Remember the value of this Planck's constant 2. It is needed what? In numericals. I will give you homework today. I'll give you what? Homework. So as to solve what the numericals. Numericals are what? Homework. Clear? Then the total amount of energy emitted or absorbed in a body. A total amount of energy. That is the third postulate. I'm talking about the third postulate. The third postulate is the total amount of energy. The total amount of energy absorbed or emitted. Absorbed or emitted. Absorbed or emitted. Absorbed or emitted in a body. Right? In a by a body, in fact, will be some whole number emitted by a body. By a body will be some whole number. It is a whole number. Some whole number. Some whole number. Multiple of. It is multiple of what? H. It It is multiple of what? H nu. E equals to H nu. Means multiple of what? H nu. Means E is equals to NH nu. E is equals to NH nu. That is his third postulate. The total amount of energy for a body which emits or absorbs radiation, that is given by, it is a whole number, it is integral multiple of what? H nu. Or else you can write E is equals to NH nu. Okay, so this is the third postulate of what? Planck's quantum theory. Okay, so there are three postulates he has given. It is also explaining what the particle nature of electromagnetic radiation. Okay, so this is Planck's quantum theory. And now, as I said, this is the first development which led Niels Bohr to propose a theory, and the second one was atomic spectra. So we got so much complication over there. It is not there in our syllabus, current syllabus. So atomic spectra, there are some types of spectra like absorption spectra and emission spectra, and those results are also helped Niels Bohr to propose what model of atom. So as I said, in spectrum, atomic spectra, we'll get two types of spectrum: emission spectrum and absorption spectrum. If you want more knowledge about those things, you can go through the definitions in what NCERT textbook. I hope all of you are having what NCERT textbooks. Clear? Okay. Then now we'll go for Bohr's model of atom, the much weighted concept. Bohr's model of atom, the structure of atom, the important concept is what? Bohr's model of atom. So in this case also, I'll rub this to Bohr's model of atom also. We are having some postulates or assumptions, you can say. Bohr has also given some of his assumptions, you can say, or else what the postulates. We'll go through one by one. Before that, we are starting our syllabus. Bohr's model of atom. Bohr's model of atom. Okay. See, Bohr's model of atom has given so many ideas regarding the structure of atom. It has given so much information regarding the structure of atom by utilizing the informations collected from what Rutherford's model of atom and J.J. Thomson's model of atom. Okay, so that is what we are supposed to discuss over here. And he also has given some assumptions, his postulates. So those postulates are to be discussed over here. Bohr's atomic model. So the first postulates of what? Bohr's model of atom. First postulate of the Bohr's atomic model. He said an electron in an atom can revolve around the nucleus. An electron in an atom can revolve around the nucleus in a circular path of fixed atom. So an electron in an atom can revolve around the nucleus in a circular path of fixed energy and radius, or fixed radius and energy. And that circular path is called as orbit. That circular path is called as what? Orbit. Right? So energy levels, you can say, those are different energy orbit or energy level with a particular amount of energy. That is his first postulate. What was his first postulate? I will write. See, the first postulate, Bohr's model of atom, is what? An electron in an atom can revolve around the nucleus. Can revolve around the nucleus in a circular path. Can revolve around a circular path of fixed radius. And energy. Fixed radius and energy. Right? These circular paths are called as what? Are called as what? Orbit. That's what I was talking about. These circular paths are called as what? Orbit. Right? And these orbitals will be having a fixed radius, and there will be a fixed amount of energy. Those are nothing but my energy levels, you can say. Those are represented by K, L, M, and energy shells. They have a particular energy. So different energy levels have a different amount of energy. Correct? So that's what his first observation. Electron can move around the nucleus in a circular path. That circular path is called as orbit. And these orbits will be having a definite energy and fixed radius. That was his first postulate, Bohr's atomic model. Okay, in Bohr's atomic model, this is the first postulate. And now let me go for the second postulate. Second postulate, Bohr's model of atom. Second postulate of Bohr's model of atom. See, energy of electron does not change with the time. He said in his second assumption, he said that energy of electron does not change with time. Correct? Do people understand? Means as long as electron stays in a particular energy level, it won't lose or it won't gain any energy. So that's what he said. It's constant energy of the electron. Energy of the electron in an orbit does not change until it gains energy and jumps to higher, or lose energy and come back to what ground state or lower state. Okay? So as long as electron is going to stay or remain in a particular orbit, there will be no change in what energy. That is his second postulate. So let's write. I will write this one. Energy of electron in an orbit does not change with I will write with what? Time. With time. Okay, so this is the arrow mark, don't get confused. So after this I have written over here with time. That's it. Clear? So the energy of electron in an orbit does not change with time. If it is going to jump, obviously it have absorbed energy. If it absorbs energy, it will jump to higher excited state. If it is going to lose energy, it will come back to what? Ground state. So as far as it is going to, as long as it is going to stay or remain in a particular orbit, there will be no change in energy of the electron. Or else you can say the energy of the electron is quantized. It is fixed, it is constant. It does not change with what? Time. Okay, so that is the second postulate. That is what? The second postulate of Bohr's model of atom. The first one was electron in an atom can revolve around the nucleus in a circular path. And that circular path is called as orbit. Means n 1, 2, 3 orbits, n 1, 2, 3, 4, n values. That is nothing but my shells, K, L, M, N, like that. Correct? See, and the third one, energy of electron in an orbit does not change with time. It does not change with what? Time. Then let us go for the third postulate. The third postulate of what? Bohr's model of atom. So in this case, in the third postulate, he said that only those orbits are permitted. Only those orbitals are permitted in which the angular momentum of electron is integral multiple of h by 2 phi. H by 2 phi. Please listen to me. The third postulate, I'm talking about what? Third postulate. I'm talking about the third postulate. What it is about orbit. It is about what? Orbit. Okay. Only those orbits are permitted in which the angular momentum of electron is an integral multiple of h by 2 phi. Only those kind of orbitals are allowed, in fact, permitted, you can say. So that is his third assumption, you can say, or that is his what? That is his what? The third postulate. Assumption is nothing but what? Postulate. The angular momentum of electron in a given stationary state can be expressed in different ways. I mean, in an equation, if we got equation, and before that, the third postulate of Bohr's atomic model, it is an integral multiple of what? H by 2 phi. Correct? So I will write that third postulate. Right? Only those orbitals, only those orbits, you can say, not orbitals in fact, only those orbits, only those orbits are permitted, only those orbits are permitted in which the angular momentum, in which the angular momentum of electron, is a whole number or multiple of, or what? Multiple of h by 2 pi. H by 2 pi. What is h here? Yes, it's a Planck's constant, h by 2 pi. So only those orbits are permitted in which whose electron, angular momentum of electron is multiple of h by 2 pi. Angular momentum is mvr. mvr is equals to h by 2 pi. mvr, v, it's not new. mvr is equals to h by 2 pi. Correct? M, mass of electron, velocity of electron, I mean speed of electron or radius of electron. Planck's constant, h by 2 pi. Integral multiple in the sense this n h by 2 pi. Only those orbits are permitted. Clear? This is the third postulate of what? Bohr's model of atom. See, in NCERT or in other textbooks, the sequence might be changed. This might be the first one, this might be the second one, this might be the third one. But the postulates are what? Same. Postulates are same, assumptions are same. The sequence of postulates or assumptions are what? Different. So this might be the first in any other textbooks. This might be the third in other textbooks. So sequence is same, but the postulates are what? Same. So this is the third postulate. So let us go for the fourth one. I will rub this for fourth. So the fourth postulate is about energy. Energy is about what? Energy. The fourth postulate is about what? Regarding the energy of the electron when it emits, when it absorbs. About energy, the frequency, you can say. Frequency of radiation absorbed or emitted when transition occurs between two stationary states. That can be expressed. That is different. See, energy in frequency, you can say. Frequency can be expressed. For what? Frequency can be expressed delta E by H. Delta E by what? H. So that is the frequency. Frequency when an electron emits or absorbs energy, what? Energy. So the frequency of that radiation absorbed or emitted when transition occurs between two stationary states, that differ in the energy by what? Delta E. See, this delta is nothing but change in energy. So that can be written as what? E2. E2 minus E1 by 1 H. Means an electron after gaining electron. For example, I am having a nucleus over here. This is my first energy level, right? And here I am having my second energy level, right? This electron, there is electron. There is an electron, right? So this will move to this state, this energy level. It will move to this state, this energy level. See, this is my E1, this is my E2. When it will jump? Only when it absorbs energy. Absorbs what? Energy. When it absorbs energy, it will move toward higher. It will come back. See, it is, if electron is going to coming back to what? Stationary. The previous or was lower energy level. It has to emit the radiation. It has to emit the energy. It has to what? Emit the energy. Here, I'll get emission of energy. See, emission of energy. Are you people understanding? Okay. So that is the fourth postulate. Okay. See, this fourth postulate can also be written as, if electron is going to absorb energy, it will move to higher excited state. If it is going to emit energy, it will come back to a lower energy state. That is the fourth postulate. It is talking about change in energy. The fourth postulate talks about what? Change in energy. Correct. So when electron jumps to a higher energy level like this, it needs energy. Energy is absorbed. If it is coming back to what lower state, lower energy level, it has to emit energy. So this change in energy is nothing but my energy level 2 stationary, level 2 from E1 to E2 it has it. So that will be my E2 minus E1. So this amount of energy is what? Change in energy. That is the energy of electron, gain or loss. So this is the fourth postulate. What is fourth postulate? You tell me. If electron jumps to a higher energy level, it absorbs energy. If it comes back to a lower energy level, it emits energy. So that is change in energy. That change in energy is written as delta E is equals to E2 minus E1. So frequency associated with that electron is expressed in this manner. Frequency is equals to delta E by N. That is nothing but E2 minus E1 by what? H. Clear? So that is the fourth postulate of what? Bohr's atomic model. So the first one was regarding orbit. Electrons revolve around the nucleus in a circular path, that is called as orbit, and those orbits will be having a fixed mass, fixed energy and fixed radius. Clear? Similarly, we were even talking about the second, the electron energy of the electron in an orbit does not change with time. That's what the fourth belongs to. Fourth is also saying the same thing. And the third one was only those orbits were permitted in which the electron, whose angular momentum of the electron is integral multiple of h by 2 phi, where h was Planck's constant. So that is nothing but mvr equals to h by 2 pi, mass of electron, speed of electron, radius of electron. mvr is angular momentum. mvr is equals to h by 2 pi or nh2 pi. nh2 pi. So that was the third. And the fourth one was this one. When electron jumps to a higher energy state, energy is absorbed. When it comes back to a lower energy state, energy is emitted. So the frequency associated with energy of that radiation is expressed in this term. Nu is equals to delta E by H. That is, delta is nothing but E2 minus E1. So this shows the energy of one electron. Okay? So these are the postulates of Bohr's model of atom, Bohr's atomic model. Then, what are the successes that this Bohr has got? The success of Bohr's model. The first one, Bohr's atomic model successfully explained the stability of atom. Successfully explained what? Stability of atom. So let me talk about the success of Bohr's atomic model. Correct. So these were the postulates. Till now we were discussing about postulates of what? Bohr's model of atom. And now success of Bohr's atomic model. Success of Bohr's atomic model. One thing it has explained, this theory has successfully explained the stability of atom. Stability of atom. Stability of atom. Correct? He has given in postulate, he said electron will be revolving around the nucleus. There will be energy, a particular energy for electron. There will be particular angular momentum for what electron. So the energy levels are having particular energy. The radius is also a particular amount. So he has explained regarding those things. So that is why I can say successfully it has explained about what? Stability of atom. Clear? So that is the first. Second thing, he successfully explained the spectral or the spectrum of hydrogen atom. Please do remember, very important. He successfully explained the spectrum of hydrogen atom, which we are going to start now. So we even need to talk about hydrogen atom, spectrum of hydrogen atom whenever it comes to what Bohr's model atom, because he has taken hydrogen and explained the spectral lines in it. He explained the spectrum of hydrogen atom. So that is his second success. Then let us go for the Bohr's model of hydrogen atom. Bohr's model of hydrogen atom. So till now we are talking in general for an atom, and now particularly about hydrogen. Bohr's model of hydrogen atom. Bohr's model of hydrogen atom. See, we got to know that when an atom gains energy, when energy is supplied, they will absorb energy, they will gain energy. So after gaining energy, they won't sit in their old energy levels, they will move toward their excited energy levels. Clear? And it is unstable. They are supposed to come back to what lower energy state so as to attain stability. So while coming back, they are supposed to emit the energy which was absorbed. So it will emit the energy in the form of what? It emits the energy in the form of what? Radiations. In the form of what? Radiations. So those radiations are having so many spectral series, spectral lines. So many spectral lines. There will be so many spectral lines. Clear? And he studied. The Bohr has studied the spectral lines of what hydrogen atom. He passed energy. He saw the spectrum of what hydrogen, and he has given his idea for the spectral of what hydrogen, spectral series of hydrogen. Okay? So when it emits the radiation while coming back, that radiation was having so many spectral lines, and he found there are some 5 spectral series, different 5 spectral series. He said that there are 5 different series of spectral lines. So I will draw that one, the spectral series of what hydrogen atom. Okay? So let me draw that. Let me draw the spectrum of what hydrogen. It consists of what? Is it visible? Yes. I'll write over here. Spectral lines. The spectral lines of what? Hydrogen. Spectral lines of hydrogen. Yeah. I'm drawing. So this, in this way we are having the wavelength lambda, and this is my energy. I'm drawing spectral lines of hydrogen. This is energy. I hope you can understand. I will write it clearly. ENERGI, energy, and this is wavelength. Okay, so this is my first energy level. This is my first energy level. See, lambda, that is nothing but wavelength. Okay? It is not visible. Or is it visible? Yes, is it visible? Clear? Lambda. Okay, so now this is my first energy state. That is n is equals to 1. First energy level. And over here, I will draw my second energy level. Over here, I will draw my second energy level. So this is my n is equals to 2. Or else you can say L shell, L energy level, K, L, M, N, so on. This is K, L, M, and so on. So here I will draw my third energy level. Here I will draw third energy level. This is my third energy level. N equals to 3. So is it going bit cross? Yes, it's bit cross. I will redraw this. It needs more time. And in the beginning only I say to people I'm not good at arts. I'm not good at drawings. I'm trying my best. Again it is going, I think. So let it be no. It is my n equals to 3. Energy level n equals to 3. Perfect. And that cross. Now, next one is what? My energy level 4. Energy level 4. 4. This is my L equals to 4. L equals to 4. And then I have L equals to 5. These are my energy levels. N equals to 5. And so on. Having N equals to 6, 7, 8, so on. Right. This might be N equal to 6. And similarly, I'll be having 7. I'll be having. These are not state, please do adjust with this. These are the different energies. See, from higher energy will be from these higher energies. See, it will lose. Electron will lose energy. This one, see, this is my. This will be up to what N equals to infinite. It will be the N up to what N equal to infinite. I don't want that one. See. Energy can be lost. Electron can fall from N2 to N1 or N3 to N1, N4 to N1, N5 to N1 or N6 to N1. Correct? So first, it will come back to what? First state. From second to first or third to first or fourth to first or fifth. Anything. So that's what I'm trying to draw over here. I'll draw. From here I'll draw. From here. From here, from here, from here, or from here, or from here. Correct. So this is a type of series of spectral lines. So this is the first series. This is what? First series. There are so many spectral lines. So that is why this is called as what? The series of spectral lines. Spectral lines. Series of spectral lines. Similarly, I'll draw another series. I'll draw another series over here. This is my second series. This is my second series. This is my second series of what? Spectral lines. Similarly, I got third two. This is third series of spectral lines. This is what? Third series of what? Spectral lines. So these are named. These are given what? Scientist names. Different spectral lines. Correct? I will talk about that. Correct? So this is another spectral series, and here obviously I will be having one more. Here I will draw those. This is also another spectral series of spectral. So this first one is called as Lyman series. This is my what? Lyman series. See, Bohr has given the spectral lines. The Bohr has given what? The spectral lines. Bohr has given the spectral lines. This is the first series, Lyman in fact. Second is called as what? Bohrs. Second is called as what? Bohrs. Okay. And the third one is called as what? Passion series. Lyman series, Bohrs series, Passion. Then bracket. This is bracket series. And the last one is P-fund. This is my P-fund series. Okay. See, in case of Lyman series, electron will lose energy and will come back to N1. It may come back from N5, N6 or N3 or N2. It will come from N2, N3, N4, N5, N6, N7. So it will come. So in case of this one, N value is 2 for what? Bohr. For Lyman N value is N1 value is what? 1. For Bohr N1 value is 2. For second state, electron may fall from N3 or N4, N5 or N6. Correct? No. So N1 value for Bohr is 2, N1 value for Lyman is 1. Similarly, for Passion, N1 value is 3. For third state, electrons can fall from what? Higher energy level. from N5, N6, N4, so on. Similarly, the same thing happens with what these spectral lines. So this is the spectral series that is explained by what Niels Bohr for hydrogen of atom. So this is how he observed. That we have a table over here for series. For example, I'm having series. Series is Lyman. Second one is what? Bohrs series. And then I'm having Paschen series. I'm having bracket. I'm having P1. So these are the series, correct? And their N1 values. Correct? So means their energy state, the stationary state of this one. So Lyman says N1 value is always what? 1. First one. Correct? For Bohrs it is 2. For Paschen 3. Bracket 4. P1 5. Clear? N1 1, 2, 3, 4, 5. These are their N1 values. Similarly, their N2 values. See, if the N1 value is 1 for Lyman, then it cannot become same for what N2. Obviously, N2 means higher energy levels. So if N1 lower energy, the main energy level stationary state is 1, first one, then it has to be 2, 3, 4, and so on. But it cannot be 1. So it might be 2 or 3 or 4 and so on. Okay. Similarly for Bohrs, it cannot be 1 or 2. It can be 3, 4, 5 and so on. Correct? So for this one, see, I'll write a bigger 3, 4, 5. Here 4, 5, 6 and so on. And here 5, 6, 7 and so on. Here 6, 7, 8 and so on. Okay, so these are the N1 values and N2 values of what these particular series. So in hydrogen spectrums, remember we got how many series of spectral lines? We got 5 series of spectral lines. One is Lyman, and then one is Bohrs, Paschen, bracket, and P1. That is what I have drawn over here. Correct. So N1 value for Lyman is 1, N value for Bohrs is 2, for Paschen 3, bracket 4, for Paschen it is 5. So N1 value and N2 value. Then region, their spectral series arises or falls in which region? Lyman were observed in which region? Yesterday we have drawn spectrum, electromagnetic spectrum, spectrum of electromagnetic radiation. We were having cosmic rays, we were having gamma rays, we were having X rays, UV. In that we got a visible region. In visible region, the range of visible region was what? From 400 nanometer to 700 nanometer. So like that, in which of those region these spectral lines falls? Where they fall? Lyman series, the spectral lines which belongs to Lyman series, based on their wavelengths and frequency wavelength or frequency, they have decided that this spectral line belongs to this spectral series belongs to this region. Like that. Similarly for Lyman, it is UV ultraviolet region. It falls in what? Ultraviolet region. For Bohrs, they falls in what? Visible region, which I have drawn yesterday. So 400 nanometer to 700, and remaining Paschen, brackets, and P1, their regions are infrared. They will fall in what? Infrared. So you please remember this table. This table you are supposed to remember. Here I have given the types of the series of what? A series of what? Different spectral lines of what? Hydrogen atom according to. This was a success. He successfully explained what? The spectrum of what? Hydrogen. Okay? This was his second success of Bohr's atomic model. Correct? So this is the spectral lines which are observed when hydrogen atoms are heated. They will absorb energy, they will move to higher energy state. It is unstable, they are supposed to come back. While coming back, they will emit energy in the form of radiation. So those radiations will be having lots of spectral lines, and those spectral lines are studied. And Bohrs said that there are 5 different series of spectral lines which have different wavelength frequency. So the wavelength frequency of Lyman is different. Wavelength frequency of Bohrs is different. fashion is different, bracket is different, free function. So he even decided based on the wavelength of those spectral lines, he said that Lyman falls in which region? UV ultraviolet region. Bohrs series falls in what? Visible region. Similarly, fashion, bracket and free function falls in what? Infrared region. So based on their wavelength and frequency. Clear. So this is about the Bohr's model of atom. The first success was it has successfully explained the stability of atom. Second one, it has successfully explained the spectrum of what? Hydrogen. Then let me talk about the third one. So we'll talk about third one too. I'll grab this before that. That is vitamins. Third one. The third success. See, by using Bohr's model of atom, we can even calculate the energy of the electron or orbit, or what? The radius 2. Here. So let me talk about the third success. The third success of what? Bohr's model of atom. So that is what Bohr's theory that helped in what? Calculating the energy of the electron. It helped us to calculate the energy of electron. Also radius. It has explained energy. It can be used to calculate energy, and also it is used to calculate what? Radius too. So he has given some equations. There are some equations. So as to calculate radius, there is a formula. That is nothing but my Rn. Rn is equals to A0 into n square. You just remember all these equations because these are needed in later classes while solving problems, while solving numericals. In NCERT they have given numericals based on what? These equations. So that is why these are very important. So radius of an orbit, Bohr's orbit, the first orbit. The equation which is used to calculate the radius for hydrogen. See, Rn is equals to A0 n square. Here the A0 value is what? 52.9 picometers. It is 52.9 picometers. 9 picometers. So this is for the first orbit, and that is why it is called as Bohr orbit. First orbit. So second orbit, n value will be different. 2 square, 3 squares, like that. So by using this one, we will calculate the radius of an orbit. Clear? Similarly, energy, En. Energy can also be calculated. Energy can also be, even not only radius, even energy can also be calculated. Energy can also be calculated by using formula En is equals to minus RH 1 by n square. 1 by what? N square. Here RH is nothing but my Rydberg constant. RH is nothing but Rydberg constant. Rydberg constant. The value of Rydberg constant, the value of this Rydberg constant is 2.18 into 10 to the power minus 18. That is the value of the Rydberg constant. You fill over here, so energy is nothing but minus 2.18 into 10 to the power minus 18, 1 by n square. So by using this Bohr's model of atom, we even got to know that we can even calculate the energy and radius orbit of orbit 2. So A0 value we are given 52.9. This is of the first state, first orbit. So that is why it is called as a Bohr orbit. It is called as a Bohr orbit. Clear? So that is the radius, and I have energy. En is equals to minus of RH 1 by n square. These are the energy level. Energy level. If it is one, see, if it is one, I will change this. If it is one, for first E1 is equals to minus 2.18 into 10 to the power minus 18 into 1 by 1 square. For 2 it is 1 by 2 square. For 3 it is 1 by 3 square. Like that. For different energy levels, for different orbits, I can calculate the energy by using this formula. I can even calculate the radius by using this formula. And it is also applied. It is also used to calculate not only hydrogen atom, even for hydrogen-like species too. Even for what? Hydrogen-like species too. Then hydrogen-like species in the sense, it should have only one electron. It should have how many? Only one electron. Plus means like helium plus. We can say helium plus is a hydrogen-like species. Yes or no? Helium plus, helium plus. Clear? Or else lithium 2 plus. Helium plus, how many electrons are there in helium? 2. Plus means I have removed one electron. After losing an electron, I will get positive charge. So helium has lost one electron. So helium plus means how many electrons are there now? Only one. Then lithium plus 2. Lithium plus, in lithium I have 3. Among those 2 electrons are removed. Now I am left with 1. So lithium is having 3. Lithium 2 plus is having 1 electron. Helium is having 2. Helium plus is having only 1. So for these kind of atoms also we can calculate. I mean, we have an equation to calculate energy as well as what? Radius. Then let us write that equation too. I'll write that equation too. See, energy of, I will write this. I will write here only. Energy of the atoms like hydrogen. Atoms like what? Hydrogen. Energy and radius can also be calculated for those two. It is 2.18 into 10 to the power minus 2.18 into 10 to the power, sorry. I'm talking about energy, first energy. That's 2.18 into 10 to the power minus 18 z square by n square. Joules. Z square by n square. So this equation is used to calculate the energy of hydrogen-like species for helium, lithium. Here Z indicates atomic number. If it is helium, 2. If it is lithium, 3. Like that. So Z square by n square. N is nothing but my energy level. N might be 1, it might be what 2, or it might be 3. So this is Z. Okay. Z square by what? N square. Energy of a orbit in case of what? Hydrogen-like atoms, hydrogen-like species. So radius 2 R. Earlier Rn was what? Epsilon naught into n square. Now it is 52.9 n square by z. This is used to calculate radius, whereas this is used to calculate what? Energy of hydrogen-like species or hydrogen-like atoms. Right? So this is the third success of what? Bohr's atomic model. This is the third success of what? Bohr's atomic model. Clear? So third, after this, we are supposed to talk about line spectrum of hydrogen. Line spectrum. In case of line spectrum of hydrogen, what we will discuss. So there, energy of what different states, energy of what different energy levels. Correct? So energy level 1 is E1, energy level 2 is E2. They are compared, and they have derived something over there. What they have derived? So I am explaining about the line spectrum of what? Hydrogen. Line spectrum of hydrogen. Here, so line spectrum of hydrogen. Line spectrum of hydrogen. See, energy of 2 different energy levels, or energy of 2 different orbits. That is nothing but my delta. It can be expressed as what? E2 minus E1. This is equation number 1. Correct? This is my equation number 1. Similarly, we even know that earlier I have written delta E is equals to, in that case nu, I was comparing that as what, delta E by what, H. Okay. By using, I can write this as what, delta E is equals to, earlier I have written about energy too. Energy was what, R H 1 by N square, minus, in fact, minus RH by 1 by N square, minus RH by 1 by N means 1, if 2, 3, 4, and so on. So this is also energy. So I will consider this too. So energy can also be written, or change in energy, same change in energy can also be according to this, this equation which I have written earlier. According to this, I can write that as what, minus of RH by N initial. See, this E2, E1 are nothing but final and initial. Alright, F and I, instead 1 and 2. Final, last energy, previous, ground. So, and final, minus of RH capital H, RH divided by Ni. RH divided by what? Ni. Here, and square, and final square, and initial square. Square you take square. So this is my equation 2. Now combine these two. Or else before that, I'll simplify it. I can even rearrange it like what? RH. So as to remove this negative charge, I will take this RH outside. RH 1 by Nf square. See, N1 1 by Nf square, 1 by Nf square minus 1 by Ni square. 1 by Nf square and 1 by what? Ni square. See, earlier it was final and initial. So now I have changed this because of this. And on rearranging, here I will get initial and here I will get final. Simple mathematics. On rearranging by taking RH outside, I will get this equation. Clear? And now I will frequency associated with energy. Frequency associated with energy. Nu is equals to delta E, change in E divided by H. Okay. So this delta E is nothing but this one. You are supposed to substitute this value over here divided by H, and you know RH value. RH value also, you know, RH is nothing but 2.18 into 10 to the power 2.18 into 10 to the power minus 18. Correct? So now divided by I got H, same, divided by H means nu is equals to this entire divided by H. This entire divided by H. H Planck's constant, that also I know, 6.626 into 10 to the power minus 34 joules. If you are calculating, so you will get this frequency. In fact, you will get this frequency as what? 3.29 means RH 2.18. Here I will write. It is 2.18 into 10 to the power minus 18 divided by H 6.626 into 10 to the power minus 34. 1 by N initial square minus 1 by N final square. Okay. So this is how we are going to write. And at last, on calculating, you will get it as 3.29 into 10 to the power 15. 1 by N initial square minus 1 by N final square. Okay. So this is in terms of what? Wave number. Sorry, frequency. In terms of wave number also we can convert this. Then what is how wave number is related? How wave number is related? You tell me. Wave number is nothing but nu bar. Nu bar is equals to what? Nu bar is equal to what you can write for nu bar? Nu bar is equals to nu by c. Nu bar equal to nu by c. And this is the value of what? Nu. You just fill this over here. You just fill this over here. No. And you know the value of cc is velocity of light. That also you know. If you are calculating, if you are supposed to express in terms of what wave number, nu bar, it comes out as play. Substitute. Nu bar is nothing but nu bar c. I have nu value over here, and you know c value. So you just substitute it. On substituting, you will get it as, I'll write somewhere over here in a small letters. I'll write nu bar is equals to 109,677. So I am supposed to delete something. I mean, I'm supposed to drop something. If it is visible over here, I can write over here. So nu bar, because it's a big equation. So nu bar is nothing but nu bar is equals to, on substituting nu value and c value over here in this case, nu bar comes out as 1.096 double 7, 1.09677 into 10 to the power 7 into 10 to the power 7, same 1 by ni square initial minus 1 by ni square initial and final ni and n. Clear? So this is in terms of wave number. This is in terms of frequency. Correct? At last I'm going to this method. This is in terms of wave number. So this is the line spectrum of hydrogen as explained. The energy of line spectrum of what hydrogen was explained. Clear? Tomorrow we'll discuss about limitations of what Bohr's atomic model. We are supposed to discuss about the limitations of Bohr. So there are 4 limitations for what Bohr's atomic model. We'll discuss those things tomorrow, and we'll finish up this Bohr's model of atom. So today we have started with Planck's quantum theory, his postulates, and then we shifted toward Bohr's model of atom. In Bohr's model of atom, we have discussed about what their postulate, his success. During his success, we said that he has explained stability. Then he explained successfully about the spectral lines about hydrogen spectrum we have discussed, and this is the third success, that is it was also very useful to calculate what he was successful in calculating what energy and radius of the atom hydrogen, and even hydrogen like species too. He has given equations. We even discussed about those. Based on that, there are numericals in what NCERT. There are 2 numericals based on those equations, and that too are solved. They have even given what solution. They have mentioned like problem number X, question, solution also they have given. Problem number 2, solution also they have given. So your work is to practice those numericals. So that is your today's homework. So based on those equations, energy and radiation, they have given some numericals in NCERT textbooks. There are 2 problems or numericals in what NCERT textbook. Please solve those. Take those things as your homework. You solve those in your home. Correct? So that practice it. They have one given solution. You just go through those things and practice them. Those are very helpful. Clear? So tomorrow, as I said, we'll start with what limitations, the disadvantages of what Bohr's model of atom. Thank you.